Hello everyone. This is Dr. Rishikesh Naravade, Assistant Professor, IIBM, and I will help you basically with understanding quantitative techniques. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding those phenomena. You know, in the business world and in every aspect of daily living, quantitative techniques play a very vital role in decision making. In order to work effectively in modern business organization, whether the organization is private or government or a state, or it can be an industry, so whatever, managers must be able to use these quantitative techniques in a confident and in a reliable manner. Accountants make decisions based on the information relating to the financial state of the organization. Economists make decisions based on the information relating to the economic framework in which the organization operates. Marketing staff make decisions based on the customer response it receives for its various products and maybe design of the products. Personnel managers make decisions based on the information relating to the levels of employment in the organization and so on. So basically mathematics is as old as humanity. Though the statistics is coined in the 17th century as one of the discipline of the mathematics, it is very new terminology. Many times in day-to-day life, we use these terms interchangeably. Statistics is basically the science of understanding data. It will help us to analyze, process, and use both types of data. That is quantitative data and qualitative data. So what exactly quantitative and qualitative data? So there are two types of variables, quantitative variable and qualitative variable. So when we can call it a variable as a quantitative variable and when we can call a variable as a qualitative variable. So quantitative variables are the variables which have actual unit of measurements. Like we can take example of height of an individual, weight of an individual, or length, or maybe product specifications, or maybe profit a company generates. So these have actual unit of measurements. So we can say that these variables are quantitative variables because these can be measured in actual units, whereas qualitative variables do not have actual unit of measurement. For example, we can talk about its beauty, or maybe scenery, or maybe customer satisfaction, or maybe employee satisfaction. So these variables do not have actual unit of measurement. So these can be measured in different categorical or qualitative kind of a measurement units. So statistical analysis, we can come across these kind of variables in all walks of life. So statistical analysis deals with both types of analysis. So we can come across this kind of data everywhere. Your shoe size, the clothes which you wear, devices which you use, or maybe internet speed at which you use, or maybe data usage, or maybe in media like TV viewership, maybe in terms of TRP ratings, or maybe the medical facilities which we use. So we can take the names and we can go across all walks of life, and you will find that there is data there. That data has been transformed into information, and there are a lot of applications, statistical applications, which are used on this data. But I must tell you, once you have hold on that statistics or maybe data analysis, it will prevent you from buying faulty arguments, maybe in terms of maybe in articles, or maybe in debates, or maybe in political discussions, or maybe through advertisements. You will be easily able to analyze and properly process that information. So companies today rely on data analysis and interpretation to drive various business decisions. They use data to enhance growth, minimize losses, and avoid failures. That's why they are willing to hire candidates with excellent quantitative aptitude. So you can see that in various campus placement drives, or maybe pool drives, or maybe recruitment and selection drives, companies filter these candidates based on quantitative aptitude tests. So wherein this quantitative aptitude is checked by the companies, and filtering criteria. Through these filtering criteria, students are shortlisted. So statistics, basically statistical knowledge will help you in every functional area you would like to work in, maybe operations, maybe in marketing, maybe in HRM, maybe in finance. So wherein we can find that people who can consume data and digest it, that information properly, will have edge over the others. So now you can see there is a rise in different kinds of analytical courses in various streams like marketing analytics, business analytics, maybe HRM analytics, financial analytics, etc. So it is always been said that management is an art and science. So the science part of the management is basically data, basically analysis of data, various statistical applications of based on that particular data. One of the renowned mathematician and biostatistician, Carl Pearson, you might have come across Carl Pearson correlation coefficient. So this Carl Pearson has said that statistics is the grammar of science. So with the help of this foundation course, we will be addressing your different skills like logical reasoning or analytical skills, or maybe how to use that data for further decision making and taking different kinds of decisions. And basically this foundation course, along with this quantitative technique papers in your subsequent curriculum, it will take you longer in your careers, in your respective careers, basically in whatever functional area you would like to work in. So now let us start this session with basics, which is for any quantitative technique, basically quantity, that is numbers. So let us start our session with numbers. And first of all, I would like to show you one video which is on numbers and history of numbers and number system. So let us see that first.
One, 2, 3, 4, 5, 6, 7, 8, 9, and 0. With just these 10 symbols, we can write any rational number imaginable. But why these particular symbols? Why 10 of them? And why do we arrange them the way we do? Numbers have been a fact of life throughout recorded history. Early humans likely counted animals in a flock or members in a tribe using body parts or tally marks. But as the complexity of life increased, along with the number of things to count, these methods were no longer sufficient. So, as they developed, different civilizations came up with ways of recording higher numbers. Many of these systems, like Greek, Hebrew, and Egyptian numerals, were just extensions of tally marks, with new symbols added to represent larger magnitudes of value. Each symbol was repeated as many times as necessary, and all were added together. Roman numerals added another twist. If a numeral appeared before one with a higher value, it would be subtracted rather than added. But even with this innovation, it was still a cumbersome method for writing large numbers. The way to a more useful and elegant system lay in something called positional notation. Previous number systems needed to draw many symbols repeatedly and invent a new symbol for each larger magnitude. But a positional system could reuse the same symbols, assigning them different values based on their position in the sequence. Several civilizations developed positional notation independently, including the Babylonians, the ancient Chinese, and the Aztecs. By the 8th century, Indian mathematicians had perfected such a system, and over the next several centuries, Arab merchants, scholars, and conquerors began to spread it into Europe. This was a decimal, or base 10 system, which could represent any number using only 10 unique glyphs. The positions of these symbols indicate different powers of 10, starting on the right and increasing as we move left. For example, the number 316 reads as 6 times 10 to the 0th power, plus 1 times 10 to the 1st power, plus 3 times 10 to the 2nd power. A key breakthrough of this system, which was also independently developed by the Mayans, was the number 0. Older positional notation systems that lacked this symbol would leave a blank in its place, making it hard to distinguish between 63 and 603, or 12 and 120. The understanding of 0 as both a value and a placeholder made for reliable and consistent notation. Of course, it's possible to use any 10 symbols to represent the numerals 0 through 9. For a long time, the glyphs varied regionally. Most scholars agree that our current digits evolved from those used in the North African Maghreb region of the Arab Empire. And by the 15th century, what we now know as the Hindu-Arabic numeral system had replaced Roman numerals in everyday life to become the most commonly used number system in the world. So why did the Hindu-Arabic system, along with so many others, use base 10? The most likely answer is the simplest. That also explains why the Aztecs used a base 20, or vigesimal system. But other bases are possible too. Babylonian numerals were sexagesimal, or base 60, and many people think that a base 12, or duodecimal system would be a good idea. Like 60, 12 is a highly composite number that can be divided by 2, 3, 4, and 6, making it much better for representing common fractions. In fact, both systems appear in our everyday lives, from how we measure degrees and time to common measurements like a dozen or a gross. And of course, the base 2, or binary system, is used in all of our digital devices, though programmers also use base 8 and base 16 for more compact notation. So the next time you use a large number, think of the massive quantity captured in just these few symbols, and see if you can come up with a different way to represent it.
I hope that video was interesting, and basically it has started with decimal systems, how the numbers are used as symbols, and then the number system, that is decimal number system, some of the number systems, and its evolution over the period of time, how it was evolved. So we'll start with our actual session now with the help of PowerPoint template presentation. So that video has given you brief overview of how that number system works and what are the different types of number systems and how over the period of time it has evolved. So now let us go one by one and let us understand. So as like decimal number system, so it has got the base of 10. So in decimal number system, we have base of 10, which has 10 symbols starting from 0, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the 10 symbols starting from 0 to 9. These are the 10 symbols which are used in the decimal number system, which has got the base of 10, that is 10 symbols. Then we have binary number system, wherein we have two symbols, base is 2, 0, and 1. So in computer systems, in computer applications, we see this binary number system is being used, which consists of 0 and 1. Then we have octal number system, wherein we have 8 symbols starting from 0 to 7, 0, 1, 2, 3, 4, 5, 6, and 7. Then we also have hexadecimal system, wherein 16 symbols are used starting from 0 to 9, which are 10 symbols. And then we have 6 alphabets starting from A to F, that is A, B, C, D, E, F. So these are the 6 alphabets and 10 symbols, that is 10 digits, that is 10 numbers, 0 to 9. So 10 plus 6 becomes our 16 symbols which are used in hexadecimal system. Now let us see that how exactly we actually use these numbers. In the video itself also it was discussed that how position of a particular number dictates its value, state its value. So I have put one example, which is 2, 3, 4, 5. So basically, you must be aware that this is the number which is stating 2345. But how we arrived at whether this number is valued at 2345? So let us consider only these these digits, 2, 3, 4, and 5. So like this, in decimal number system, which is widely applicable, we are also working in decimal number system, wherein these 10 symbols, if we rearrange them in different positions, we will get infinite numbers. So this number will talk about 2345. 5 is the number which is at units place. 4 is at tens place. Number 3 is at hundreds place. And number 2 is at thousands place. So basically, these numbers have positional value. What are these positions? Unit position, tens position, hundreds position, thousand position. So like this, so on, we can go on, and this positional value of a particular number we can determine. Now, how this 2345 number comes? Like we were talking about, it has got positional value. So units place number has to be multiplied by 1, which is 10 raised to 0. So any number raised to 0, that is exponential, that is power of 0, will give the 1. So 10 raised to 0 is 1, so which comes down to 1. 5 into 1 becomes 5. Then the tens place, we have to multiply this number by 10. So 10 into 4 becomes 40. Then we have 3 at hundreds place. We have to multiply hundreds place number with 100, which is 10 raised to 2. 2 is at thousand place. So this number, this position has to be multiplied. This number has to be multiplied by 1000, which is 10 raised to 3. So like this, it is represented in this particular format, which is 2 into 10 raised to 3 plus 3 into 10 raised to 2 plus 4 into 10 raised to 1 plus 5 into 10 raised to 0, which comes down to 5. 4 into 10 becomes 40, 3 into 100 becomes 300, 2 into 1000 becomes 2000. So we have 2000 plus 300 plus 40 plus 5, which gives me number as 2345. So like this, we can have n number of numbers, we can have infinite numbers, and these numbers, these 10 symbols 0 to 9 will have its own value based on position it has. So if it is at units place, if it has tens place, hundreds place, thousand place, or maybe millions place. So like this, we can evolve, or we can generate numbers, and how the value of a number can be generated based on its position we have seen. Let's consider another example. Let's say the next number is 45. So this 45 number, basically, it has 2 digits, 4 and 5. 5 is at units place, 4 is at tens place. So basically, this number becomes 4 into 10 plus 5 into 1, which gives me 40 plus 5, which is 45. So this is how we can determine the number and its value based on the position, the digit it has. Now let us go ahead. Now let us understand. Now basically in the previous slide we have learned what are the different types of decimal, what are the different types of number systems, not decimal, but which is one of the type of number system, decimal number system. Then we have seen the binary number system, and it has got various applications. But in day-to-day life, in real life, most of the times we come across a decimal number system which we are using. Now let us go ahead and try to see what are the different types of numbers. Now this basically image will tell you the different kinds of numbers, different types of numbers. So now let us understand natural numbers first. So the natural numbers, it is a set of positive counting numbers. So what exactly it is? So it is basically the numbers which are positive numbers, and with the help of these numbers we can count. So like I have 2 mangoes, I have 3 apples, I have 5 bananas, I have 6 shoes. Like this, these are used for counting. So initially when numbers were evolved, during that time we used to count, and for counting purpose these numbers were used, and these numbers are called as natural numbers. It does not have 0. Counting starts at 1. So it is 1, 2, 3, 4 and so on. So these numbers are called as natural numbers. Then we have whole numbers. By inclusion of 0 into natural numbers, so by inclusion of 0 into natural numbers, we get whole numbers. So whatever natural numbers are, if we include 0 in it, it becomes whole numbers. Now, what are integers? Integers also include negative numbers. Like we can see, integer which is represented by the symbol of I, -3, -2, -1, 0, 1, 2, 3. This is a mistake wherein -0 is written. So it is a typing mistake, but we can see that these are the integers. What are these integers? So integers include negative numbers. So integers are whole numbers along with negative numbers. So these are the integers, wherein we can see that these are positive numbers. We have 0, and then we have negative numbers which are negative integers. So with the help of this diagram, we also can see, so natural numbers are the counting numbers, also called as counting numbers. It starts from 1, that is 1, 2, 3, 4, 5 and so on. By inclusion of 0 in it, it becomes whole number. If we include negative numbers into these numbers, then it becomes integers. Now these integers also can be classified into positive integer. These are the positive numbers. Negative integers, these are the negative numbers. And 0 is also called as neutral integer. It does not have any value, even if it is a positive, even if it is negative. So it has got no sign at all. It doesn't make any sense even if we include positive 0, or if we add 0, or if we subtract 0. So 0 becomes neutral integer. So we have positive integer, we have neutral integer, and we have negative integers. So natural numbers, will brief again summarize. Natural numbers, these are counting numbers starting from 1 to 9, or maybe subsequently. We can proceed with the counting numbers. Then if we include 0 in natural number, then it becomes whole number. Then if we include negative numbers into whole numbers, then it becomes integers. Now let us understand rational numbers and irrational numbers. So what is rational numbers? So the rational number are the numbers which can be represented in the form of a divided by b, where a and b both are integers. Let us understand once again. What is rational number? Rational numbers are the numbers which can be represented in the form of a by b, that is 1 by 2, or a divided by b, or 7 by 9, wherein a and b both are integers and your b, which is denominator, should not be equal to 0. If any number which can be represented in the form of a by b, wherein b is not equal to 0, then automatically this number can be called as rational number. So what are the examples? Like I have mentioned here, 1 by 2. So our a is 1, b is 2. 3 by 4, where a is 3 and b is 4, that is numerator is 3 and denominator is 4. 7 by 12, even we can include negative numbers. Why? Because integer includes negative numbers also, like in the previous slides we have seen. So minus 1 by 3 is also a rational number. You can see the other examples, 8 and 7. Are these rational numbers? These are obviously positive integers. But if we take 8, it automatically is nothing but 8 divided by 1. If we consider 3, it is 3 divided by 1, which is 3. So it can be represented in the form of a by b, wherein my b is 1, that is 3 by 1. My b is 1, which is not equal to 0. What if my b is 0? Let us say 2 divided by 0. The number becomes infinite. So we are not sure what kind of number it is. So basically, a rational number, I would like to revise this again. A rational number is a number which can be represented in the form of a divided by b, where a and b both are integers and b is not equal to 0. Now let us understand more of rational number. Sometimes when the number is represented in the form of a by b, then that valuation of that number sometimes can be terminating, sometimes can be non-terminating. What exactly terminating and non-terminating? What is 1 by 2? If we actually divide and find out the value of 1 by 2, it comes down to 0.5. There is no further divisions. There are no further decimal places. 1.50, finish. We cannot compute more. The division is clear. The remainder is 0. So we have actually exactly divided that number, which is 1 by 2, which gives us value as 0.5. Same way, if we consider 1 by 4, a rational number which is in the form of a by b, and b is not equal to 0, which is 1 by 4. What is the valuation of 1 by 4? It is 0.25. So these kinds of rational numbers which are represented in the form of a by b, where b is not equal to 0, the ratio or the number is terminating. It is able to have exact division. The remainder is 0 always. Whereas sometimes we come across certain kinds of rational numbers wherein we find that these are not terminating. Let us see 1 by 3. If we actually try to divide 1 by 3, we can go on dividing this number 1 by 3 as 0.3. The remainder is 3 times 3 is 9. So 10 minus 9 becomes your 1. Then automatically we have to, because remainder is 1, remainder is not 0, we have to go on doing the same calculation again. So it will become 10. Again, if we try to divide it, it will go on 3. Again, we will have remainder 1. Again, we can divide it by 3. 3 times 3, that is 9. Again 3. So it is never ending. So this kind of number is called as a non-terminating number, which is basically the decimal places are repeating again, and it is called as a recurring, because only 3 is coming again and again and again and again. So that digit is recurring. So this kind of number which is non-terminating can also be called as a rational number. So basically this is one of the feature of rational number. So rational number can be of terminating type, can be of a non-terminating type. But if it is non-terminating type, then the decimal place value will be repeated again and again. So that's why it is called as a non-terminating and recurring rational number. Now let us see irrational number. So irrational numbers are the numbers which cannot be expressed in the form of a by b, where b is not equal to 0. Like we have seen the rational number, it is exactly opposite, which is not part of rational becomes irrational. So what is irrational number? These numbers cannot be represented in the form of a by b, where b is not equal to 0. What are the examples of this? We can see square root of 2. If we actually try to calculate the value of square root of 2, we will not be able to form that number in exact a by b form. Same way, square root of 3. What are the valuation comes across? Like if I have the valuation as 0.25, if I have the valuation as 0.25, then I can convert this fractional value or decimal value into a by b form, which is 1 by 4. So this 0.25 I can put it in the form of a by b, which is 1 by 4. But if I calculate square root of 2 value or square root of 3 value, then I cannot convert that into a by b form. And if at all I have such kind of numbers wherein I cannot convert them, I cannot express them, I cannot represent them in the form of a by b, then these numbers are called as irrational numbers. So another example, famous example, which is pi, which is valuating at 3.1415. The number goes on. This is non-terminating. So irrational numbers, we can say that it is one of the feature of irrational number, that the irrational numbers are always non-terminating and non-recurring. Like in previous case, like we were seeing 1 by 3 becomes 0.333333 and it goes on. So 3 number is getting repeated. Whereas for irrational numbers, these digits are not repeated. Every time we will come across a new number, again a new number. So it will go on repeating. So these kinds of numbers, this kind of behavior is basically non-recurring. Okay, so irrational number is always non-terminating and non-recurring number. So now I hope you have understood this, that natural numbers, these are counting numbers. Inclusion of 0 in it becomes whole numbers. Inclusion of negative numbers in whole numbers becomes integers. What are rational numbers? Rational numbers are the numbers which can be represented in the form of a by b, wherein b is not equal to 0 becomes your rational number. And rational numbers are always can be of terminating and non-terminating type, but these are non-recurring type. Whereas irrational numbers are the numbers which cannot be represented in the form of a by b, where b is not equal to 0, and these are always non-terminating and non-recurring type of number. And all these numbers are called as real numbers. So what are real numbers? Real numbers are the numbers which are used to represent maybe height of an individual, maybe weight of an individual, maybe sales, maybe profit. So you can take any kind of a form of a particular number. It will give you the real numbers. These numbers are the real numbers because it can go on, take on any values, and it will represent the real facts of the nature. Now we can go ahead with, again, there are even odd numbers, prime numbers, composite numbers. So let us go ahead and let us discuss. These are basics. You must have learned them, but this is just a revision because this is a foundation course. So we will try to again brief about basics. Some of you might be commerce graduate students, some of you might be arts graduate students, some of you might be pharmacy, some of you might be engineering graduate students. So this foundation course will try to basically address all those. So this slide basically is talking about even odd numbers. So what are even and what are odd numbers? Even numbers are the numbers which are exactly divided by 2. These numbers are called as even numbers. The numbers which are not exactly divided by 2 are called as odd numbers. So you can see 1 is odd, 2 is exactly divided by 2, so it becomes even. 3 is not exactly divided by 2, so it becomes odd. 4 is even, 5 is odd, 6 is even, 7 is odd, 8 is even, 9 is odd. Same way, we can have the negative numbers also. -1 is odd, -2 is even, -3 is odd, -4 is even. Why 0 is even? Even though there is different kinds of thoughts of schools wherein it is stated that 0 is neither even, neither odd. But there is congruence between different statisticians, different mathematicians, that 0 is even. Why it is even? Because it is fulfilling 2 conditions. 0 cannot be exactly, 0 is exactly divided by 2, and 0 comes in between 2 odds. Like we see 5 and 7 are odd, and the number in between is become even. So same way, -1 is odd, +1 is odd. So in between number is even. So as it is fulfilling 2 conditions, most of the mathematicians and statisticians believe that 0 is even number. So we'll go ahead with the same thing. So 0 is even, 1 is odd, 2 is even. So if the number is exactly divided by 2, it becomes even. If the number is not exactly divided by 2, then it becomes odd number. Now let us understand consecutive positive integers, which are basically like 1, 2, 3, 4, how it can be represented. If we consider n as a particular number, how we can generate consecutive integers, positive integers. In addition to that number is n, n plus 1, n plus 2, n plus 3, n plus 4, and it goes on. So these are consecutive positive integers. Then we have consecutive even integers. How to arrive, how to get those even integers? If our n is even, that is 2, then 2, 4, 6, 8. How we come across this is, if we treat n as 2, then it automatically becomes n plus 2, n plus 4, n plus 6, n plus 8, n plus 10 will give you consecutive even integers. Then we have consecutive odd integers like 1, 3, 5, 7. How we can generate them? If we treat n as our 1, or if we can treat n as our 13. So 13 plus 2, 15. 15 plus 2, 17. 17 plus 2, 19. The same way, 13 plus 2, 15. 13 plus 4, 17. 13 plus 6, 19. 13 plus 8, 21. Like this, we can go on and find out or get our consecutive odd integers. Now, let us understand what exactly even and odd and multiplication, addition of that. Like if n is even, n plus 1 becomes odd, n plus 2 becomes even, n plus 3 becomes odd. Same way, if n is even, then n minus 1 becomes odd, n minus 2 becomes even, n minus 3 becomes odd. Same way, if n is odd, then n plus 1 becomes even, n plus 2 becomes odd, n plus 3 becomes even. Same way, n minus 1 becomes even because n is odd, n minus 2 becomes odd, and n minus 3 becomes even. Now let us understand the rules, addition and multiplication rules. So even plus minus even gives even numbers. That is 2 plus 4 is 6. 4 minus 2 gives 2. So even if we add or subtract even number from a even number, it will give me even number only. That is 2 minus 4. It will give me minus 2. Minus 2 is even number. If we add even number into odd, then it will give me odd number. And even if we subtract even number from odd number, then also it will give me odd number. 5 plus 2 gives me 7, which is odd. 5 minus 2 gives me 3, which is also odd number. Same way, even plus minus odd gives me odd. 2 plus 2 gives me, 2 plus 3 gives me 5. 2 minus 3 gives me minus 3, which is odd. So odd plus minus odd, which is 3 plus 5 gives me 8, which is even. 3 minus 5 gives me minus 2, which is even. Now let us understand multiplication. Even into even gives me even number. 2 into 4 is 8. Odd into even gives me even. What is odd? 3 into 2 gives me 6, which is even. Even into odd is even. So 4 into 3 gives me 12. Odd into odd is equal to odd. So here 3 into 3 gives me 9. 3 into 5 gives me 15, which is odd number. So here we can see that even if we multiply even or odd even odd, it gives me only even number. But if when we multiply odd with another odd number, then we get the final number as odd number only. So I hope you have understood these even and odd numbers. I'll summarize again for you. If the number is divisible, exactly divisible by 2, then it becomes even number. If it is not exactly divisible by 2, it becomes odd number. And we have seen the multiplication and addition rules. Now let us understand prime numbers. So what are prime numbers? Prime numbers are natural numbers which are greater than 1 and that has no positive divisors other than 1 and number itself. Let us understand with the help of some numbers. So 2 is a prime number. So what is 2? 2 is the number which is a natural number greater than 1, obviously, that has no positive divisors other than 1 and number itself. So 2 can be divided by 2 and 1 only. Let us get an example of 11. So 11 is a prime number. Why it is a prime number? It is greater than 1. It is a natural number. It is greater than 1. And it has got only 2 divisors, which is 1, because 11 is exactly divided by 1, gives me 11. And the other divisor of this 11 is that 11 number itself. We don't have any divisor other than 1 and other than this number itself. So these kinds of numbers are called as prime numbers. So prime numbers are numbers which are natural numbers, which are greater than 1, which has no positive divisors other than 1 or that number itself. So these numbers are called as prime numbers. Now what are composite numbers? So composite numbers are the numbers, these are the positive integers that can be formed by multiplying 2 smaller positive integers. Let us understand this definition again. So it is a composite number, is a positive integer that can be formed by multiplying 2 smaller positive integers. What is integer? 1, 2, 3. Integers may include negative numbers also. But now, with the help of this composite number, what we are trying to understand is we are using positive integers. That is 1, 2, 3, 4. So a composite integer when is formed when we are multiplying two smaller positive integers. That is 2 into 3 becomes 6. So this is a composite number. Now, how also we can see one of the characteristics it has is it is a positive integer that has at least one divisor other than 1 and number itself. What we have seen in the prime number? Prime number was the number which does not have any divisor other than 1 and number itself. Whereas for composite number, we can say that it has at least one divisor other than 1 and that number itself. So it has got at least 3 divisors. Number 1, that number itself, and the other number can be one of the divisor. Like let's say 2 into 3 becomes 6. So 6 is composite number. Why? Because it has got 4 divisors. So 1 is obviously a divisor. That number itself, that is 6, is also a divisor. But other than these two numbers, 6 has 2 more divisors, which are 2 and 3. So 6 can be exactly divided by 2. 6 also can be exactly divided by 3. Now how this 2 and 3? These are the actual smaller integers. So if you take any number, that number will have at least 2 divisors, 1 and that number itself. If there is no other divisor, then we call it as a prime number. If it has got another or more than 2 divisors, then obviously it is called as a composite number. Let's take another example, 4 by 4, which is 16. So these smaller integers, it becomes composite number, which is 16. Now this 16 is obviously have 2 divisors, basic divisors, which is 1 and which is that number itself, which is 16. Now other than that, how many divisors it can have? That is 2 can be 2 is the divisor of 16. 4 is also divisor of 16. 4 also can be exactly divide 16 number. 8 is also exactly dividing 16. So this 16 number has total 5 divisors. Out of them, 1 and number itself are the 2 divisors, and other than that, 2, 4, 8 are the other divisors. So this is how we know that this is a composite number. If that number has at least one divisor other than 1 and that number itself, it gives us composite numbers. Now, how to count the integers? If I say there are how many digits from 0 to 39? If I say there are how many numbers in between 0 to 999? How to calculate that? Or 0 to 659? Or let's say 11 to 759. How many digits are there? How many numbers are there? Now, how to count them is with the help of this. Now, how exactly we count is subtract the smallest number from largest number and add 1 to that valuation. It will give us the count of integers, count of numbers in between that range. Let's say I want to find out the numbers between 11 and 15. So for illustration purpose, we have taken the small example 11, 12, 13, 14, 15. So how we can count these numbers? 15 minus 11 gives me 4, plus we have to add 1, which will give me 4 plus 1 as 5. So there are 5 numbers. How? So this is 11 is 1, 12 is 2, 13 is 3, 14 is 4, 15 is 5. So it will give me 5 numbers. Same way, we can count numbers between 11 to 19. So what we have to do? 19 minus 11, it will give me 8, plus 1 will give me 9. So if you actually try to calculate that, So 11 to 19. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 numbers. How we calculated that? 19 minus 11 will give me 8. 8 plus 1 will give me 9. So these are the 9 numbers. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is how we can calculate. This is how we can count. The numbers are in between the range. So I want to calculate the numbers between 11 and 750. So 750 minus 11 plus 1 will give me the numbers in between that range. Now let us understand powers. Now what exactly power is? So let's say, like we were talking about initially while description of the number 2345. So 5 into 10 raised to 0. Any number raised to 0, any number raised to power of 0 will give me 1. Same way, 2 raised to 0 is 1. 10 raised to 2 is 10 into 2. Now let us understand 10 into 10. Let us understand what exactly power is. The power of a number shows how many times to use the number in a multiplication. So if it is 10 raised to 2, so we have to use this number 10 2 times for getting the valuation of 10 raised to 2. So what is 10 raised to 2? 10 into 10 will give me 100. So that is 10 raised to 2 is 100. 10 raised to 3 is 1000. How? 10 into 10 into 10. 10 into 10 is 100. 100 into 10 is 1000. So 1000 has 3 zeros. 10 raised to 3. What is that? So 3 number of times we have to multiply. We have to use 10 for the multiplication purpose. If it is 10 raised to 5, so 10 into 10 into 10 into 10 into 10. 5 times you have to multiply 10 so that we will have 10 raised to 5. Same way, 2 raised to 0 is 1. 2 raised to 1 is only, we have to multiply only once. So that is 2 into 1 is 2. 2 raised to 2. So 2 into 2. 2 raised to 3. 2 into 2 into 2. 2 raised to 10. So we have to use 2 10 times for multiplication and getting the valuation of 2 raised to 10. This is what is the power. This is what is the meaning of the power. So power is nothing but the number shows how many times to use the number in a multiplication so that we will have the actual valuation. Now there can be the indices or powers wherein we find that 0 indices. So n raised to 0 is automatically 1 where n is not equal to 0. If it is 0 raised to 0, then it is undefined. Like we were talking about a upon b where b is not equal to 0. That is 2 divided by 0 is infinite. We are unable to compute that. Same way, 0 raised to 0, again undefined, we cannot compute that. So 0 indices wherein 0 raised to 0 is automatically undefined, but any number raised to 0 will always give me 1 where your n should not be equal to 0. If it is 0, then automatically it becomes 0 raised to 0, which is undefined. And if we calculate 0 raised to n, that is 0 raised to 1, 0 raised to 2, 0 raised to 10, 0 raised to 100, it will automatically give me value of 0, where obviously n is greater than 0. Because if it is 0, then automatically it will become 0 raised to 0. Wherein 0 raised to, if it is n is 0, then automatically 0 raised to 0, which is undefined. So we have learned in this slide, 0 raised to n becomes 0. Whatever the n is greater than 0, that is obviously 1, 2, 3, and it can go on. N raised to 0, where n is not equal to 0, then it becomes 1. And 0 raised to 0 becomes undefined. We cannot define it. Now let us learn addition of powers. So how we can add the numbers which has got powers. So this, with the help of this example wherein a raised to m plus a raised to m if our base is common and our indices, that is power, is also common. Then if we are adding these two numbers, that is a raised to m plus a raised to m gives me 2 times a raised to m. What we are doing, a raised to m, because base is same and power is also same, we are multiplying 2 times a raised to m. Let's just understand with example so that you can understand more in more clarity. So 2 raised to 3 plus 2 raised to 3, which gives me 2 times 2 raised to 3. How that is possible? So let us learn. Let us see the next step. So 2 raised to 3. What is any number raised to power, which is how many times we have to use that number for multiplication. So it is 2 raised to 3. So 3 times we have to use 2 for getting the valuation of 2 raised to 3. So it is 2 into 2 into 2. That is 2 raised to 3. Plus 2 raised to 3 again. So 2 into 2 into 2. If we calculate this, 2 times 2 times 2. So 2 times 2 is 4. 4 times 2 is 8. This is 8. 2 times 2 plus, 2 times 2 is 4. Into 2 times is become 8. So again it is 8. So 8 plus 8 gives me 16. Now what exactly we have done? 2 times 3 plus 2 times 3 is equal to 2 times 2 raised to 3, which is 2 raised to 3 is how much? We have calculated 8. So 8 times 2, which is 16. So this is one of the basic rule when we have base, a common base, and when we have same power, then we can simply do the addition of this in a 2 times a raised to m. Now let us understand what if the base is not common. So a raised to m plus b raised to m, then it will not give me a plus b raised to m. Also, it will not be possible that we will go ahead with like 2 times a raised to m or b raised to m, because base is not common. Now let us prove this with the help of actual example. So 2 raised to 3 plus 3 raised to 3 is not equal to 2 plus 3, which is 5 raised to 3. So what is 2 raised to 3? 2 into 2 into 2 plus 3 raised to 3, 3 into 3 into 3. So 2 into 2 into 2 is 8. 3 into 3 into 3 is 27. So 8 plus 27 will give me 35. What if we do this? 2 plus 3 raised to 3, then it is 5 raised to 3. 5 times 5 gives me 25. 25 times 5 gives me 125. So 125 is not equal to 35. So this we have to understand that if a raised to m plus b raised to m, then we cannot simply do this calculation as a plus b raised to m. This is not possible. Now, how to solve this then? If we want to solve this 2 raised to 3 plus 3 raised to 3, then simply what we have to do, we have to simply go on do the actual calculation, that is 2 into 2 into 2 plus 3 into 3 into 3, get the calculation and you will get the valuation. As simple as that. Now we have considered the different base. What if the base is same? Let us say a raised to m plus a raised to n or a raised to p. If the power is not same but base is same, then also we have to follow the same procedure. We have to individually calculate a raised to m and a raised plus a raised to p. So a raised to m plus a raised to p, we have to calculate them, we have to solve them individually, and then we have to add them together. Now let us understand subtraction of power. A raised to m minus a raised to m, if wherein base is common and power is also common, then obviously it will become 0. So a raised to m minus a raised to m will give me the value at 0. So 2 raised to 3 minus 2 raised to 3 Even if we calculate 2 raised to 3 is 8, 2 raised to minus 2 raised to 3 is again 8. So 8 minus 8 will give me value as 0. Now, what if the base is not common? So a raised to m minus b raised to m, it will not give me the value as a minus b raised to m. As we tend to see that the powers are equal, that is power is m. But still, as the base is not same, it is not possible for us to do this subtraction, that is a minus b raised to m. Let us see with the example. 2 cube minus 3 cube is not equal to 2 minus 3 cube. So what if the base is not common? What if the power is also not common? Simply we have to do that individual, solve that particular power, and we have to find out the valuation for that particular number. Now let us understand multiplication of powers. So a raised to m into a raised to n will give me a raised to m plus n. So which is 2 raised to 2. Let us see with the example. So 2 raised to 2 plus, into 2 raised to 3 gives me 2 raised to 2 plus 3, which is 5. So this has been solved here and demonstrated. 2 raised to 2 is 2 into 2. 2 raised to 3 is 2 into 2 into 2, which is 2 into 2 into 2 into 2 into 2 will give me 2 raised to 5. What if base is not common? Again, simply you have to do the individual calculations of those powers and get the valuation. Division of powers. A raised to m divided by a raised to n is equal to a raised to m minus n. Now, how is that? So let us understand with the example. 2 cube divided by 2 square will give me 2 raised to 3 minus 2, which is 2. 3 minus 2 is 1, which is 2. So even if we do the actual calculation like it is demonstrated, 2 cube, that is 2 into 2 into 2. 2 square, that is 2 into 2. Automatically it will give me value as only 2. So for the division of powers, what we can do is any number which is, let's say, a raised to m divided by a raised to n. The base is common, so we can use that common base and we have to just subtract the powers, that is m minus n. Let us say if the base is not common, a raised to m divided by b raised to n, then it is not possible to convert them into this form. Simply what we have to do, again we have to calculate a raised to m and b raised to n, solve that particular individual powers and divide and do the calculation, and you will get the number, you will get the valuation. Now tell me, is this correct or not? So a raised to k plus 1 is equal to a into a raised to k. Whether this is right? Here what you can see is a is a common base. The power is k plus 1, which is, we can, if we divide them, then we can see that a raised to k into a. How we do this is, as the base is common, which is a, what we can do when we are multiplying is this particular a has 1 power, this particular a has k power, so we can add this. And yes, this is absolutely correct, that a raised to k plus 1 will automatically give me a into a raised to k. What about the second one? A raised to k minus 1, like we have seen the division rule, a raised to k divided by a raised to 1. Is it right? So yes, it is absolutely right. When we have a raised to k, divided by a raised to 1, then we can as the base is common, which is a, we can say that a raised to k upon a raised to 1 is exactly equal to a raised to k minus 1.